Welcome to 9-2. This section presents methods for using sample data from two independent samples and we're going to use that to test hypotheses made about two population means, or we're also going to be able to construct confidence interval estimates of the difference between two population means. Independent. Two samples are independent if the sample values from one population is not related to or somehow naturally paired or matched with the sample value from the other population. Two samples are dependent or consist of matched pairs if the sample values are somehow matched, where the matching is based on some inherent relationship. Independent samples, heights of men and women. In Appendix B, we include the following heights of samples of men and women, and the two samplers are not matched according to some inherent relationship. There's just this sample that we've taken of men and a separate sample that we've taken of women, and they don't know each other. They're not related in any way. Those are independent. They are actually two independent samples that just happen to be listed in a way that might cause us to incorrectly think they're matched. They're not matched. As opposed to a dependent sample, heights of husbands and wives. Students of the author collected data consisting of the heights in centimeters of husbands and the heights in centimeters of their wives. 5 of those pairs of heights are listed below. These two samples are dependent because the height of each husband is matched with the height of his wife. Maybe in general, tall men have taller wives. Shorter men would have shorter wives. That pairing does mean something as opposed to just heights of men and heights of women who don't even really know each other. The hint. If the two samples are different sample sizes with no missing data, they must be independent. We can't have something that's dependent and have different sample sizes because how do we pair them? If the two samples have the same sample size, the samples may or may not be independent. Are these samples dependent on each other? If the sample sizes are different, they have to be independent. We have our objective. We can conduct a hypothesis test of a claim about two independent population means. And a confidence interval. We can construct a confidence interval estimate of the difference between the two independent population means. Our notation is going to be the same notation we've had before. A second sample, a second population, and we have the same notation, only sub 2 instead of sub 1. Our requirements. The values of sigma 1 and sigma 2 are unknown, and we do not assume they are equal. The two samples are independent. Both samples are simple random samples, and either or both of the following conditions are satisfied. The two samples are both large, N1 and N2 are both greater than 30, or both samples come from populations having normal distributions. Equivalent methods. The p-value method of hypothesis testing, the critical value method of hypothesis testing, and confidence intervals all use the same distribution and standard error. They are equivalent in the sense that they will all result in the same conclusions. Example, are male professors and female professors rated differently by students? Listed below are student course evaluation scores for courses taught by female professors and male professors. We're going to use a 0.05 significance level to test the claim. Remember the claim that the two samples are from populations with the same mean. Does there appear to be a difference in evaluation scores of courses taught by female professors and male professors? The first are requirements. The values of sigma 1 and sigma 2 are unknown. The two samples are independent. Both samples are simple random samples, and both samples come from populations having normal distributions. The null hypothesis and our alternative. hypothesis. We have these two different means. Is mu1 equal to mu2? Or mu1 minus mu2 equals 0. These are the same. If they're equal, then if I subtract them, we get 0. The alternative for this, the claim that the two samples are from populations with the same mean. It doesn't say anything about greater than or less than, so it must be that it's not equal. I go here to stat, t-stats, to sample with data. Sample 1 is var1, sample 2 is var2, mu1 minus mu2 is equal to 0. This is a two-tailed test because I either have 0 or not 0. I can have information at this end, or I can have information at this side. If it was greater than, then I would only have a one-tailed test. If it was less than, I would only have a one-tailed test. I want my hypothesis test for this. I hit compute, and here's my information. We have our t-stat, and we have our p-value. Look how big our p-value is. We fail to reject our null hypothesis. Because our p-value is big, our p-value is greater than our significance level. Therefore, we fail to reject. We could also use a critical value method. The critical value method of testing a claim about two means is generally easier than the p-value method. I have 12 pieces of data for N1, and I have 15 pieces of data for N2. And the number of degrees of freedom, always we take the smaller value and subtract 1. That gives us 11. And our alpha is equal to 0.05. In two tails, we have 0.025 in each tail. If we want to find out what the t is there, we can go to stat, calculators, t, and I have 11 degrees of freedom. I want to know what my t value is on the left side. It's going to give me a negative number. We get a critical value of t equals plus or minus 2.201, which is what we have here. Because it's two-tailed, I could also do greater than and put in 0.25. And I'll get the same exact value, only positive. My test statistic, which is negative 0.660, is in the rejection area, and this is in the fail to reject area. And that's where my test statistic falls. The test statistic falls between the critical values. These are my critical values. The numbers are a little different here. I'm assuming they got that from a chart instead of technology. The test statistic is not in the critical region, and we fail to reject the null hypothesis. I want to give you this formula, not because you're going to use it, because I do want to show you what's happening behind the scenes. We have our confidence interval, and what we're trying to show is that the difference in population means, because they're mu's, is the difference in the sample means, plus or minus this error. And this is how we get our error value. We're not going to be using the formula, but I did want to show you, let's say E equals 2 and X1 bar equals 10 and X2 bar equals 5. I would have for my interval 10 minus 5, which is 5, minus 2, and 10 minus 5, which is 5, plus 2. I know that the difference in my population means is going to be somewhere between 3 and 5. I have a certain confidence that it's going to be between those two values. Another example, we're going to use confidence interval for male and female course evaluation scores. Using the previous data, which we already have here, we're going to construct a 95% confidence interval estimate of the difference between the mean course evaluation scores for female professors and the mean course evaluation score for male professors. I go stat, t-stat, to sample with data, same as before, bar 1, bar 2, and now I'm doing a confidence interval. This is a two-tailed test. I'll have some part of it here and some part of it here. We call this alpha over 2 and this alpha over 2. Since what we have is two samples, we put in our full confidence interval, which is 0.95, and we hit compute, and we get our lower limit and our upper limit. We are 95% confident that the limits of negative 5.28 and 0.275 actually do contain the difference between the two population means. Because those limits contain 0, I can see that one's negative and one's positive. That's my lower limit and my upper limit. Between those two, 0 exists. That means I can't really reject the fact that they could be equal. Because if they were equal, then mu1 minus mu2 would equal 0. And 0 is in this confidence interval. The confidence interval suggests there is not a significant difference between the mean course evaluation scores for female and the mean course evaluation scores for male professors because it contains 0.